So my presentation will be mostly focusing around the way we are approaching augmented reality through what we call natural user interaction, which usually we summarize using the three-letter acronym NUI. So let's start by imagining that we are in year 2020, and this is a very short and very simple video illustrating our vision as far as user interaction is concerned in day-to-day life, mixing work and personal life at the same time. So we believe that in 2020, all of that has been presented will be feasible. We know almost everything on how to get there, but we are not still at the point where everything will be working the way it has been described in this video. So what I will be trying to do in this presentation is to exchange with you on various projects. Those projects are being done within Microsoft Research, and those projects are the way we think that what has been presented will be feasible. So let's start by the beginning. If you look at the way we have been interacting with computers since 50 years, it is quite clear that human and computer are slowly but merely approaching towards together. 50 years ago, you had mainframes where you have a very big computer sitting in a computer room, and the only way to interact with this computer was through punch cards, and you get listings outside of the computer room. So in fact, the computer environment was completely separated from the human. And slowly we have been able to make sure that we move into a world where the interaction between the human and the computer is more and more implicit towards what we could call or name natural computing, with increasingly natural interfaces where we wear a lot of computers every day. So I guess you have all at least one, perhaps two or three computers with you today. So there is more and more embedded intelligence in every object. We are moving also to an object-to-object environment. And all this is working through and due to this ubiquitous network access that is provided by the internet. And as we are moving in this environment, perhaps 10, 20 or 50 years from now, computers will become completely invisible. So the goal is basically to make sure that this will happen someday. So perhaps computing will become as friendly, as transparent as water, electricity, or telephone is currently used in our day-to-day life. In order to go there are a lot of transformational trends, which I'm not going to go into more details there. But it is quite clear that this natural interaction on which I will spend most of my time here will rely on many other trends, like data explosion. I will talk a little bit about the importance of machine learning in the near future. And it is clear that, as an example, Kinect, the Kinect sensor, will not be able to work like it is today without machine learning. Same thing with cloud computing. The fact that you can start a game on your Windows Phone device today and continue this game, the same game at the same place on your Xbox, rely on the cloud computing being accessible everywhere, and you are able to, in fact, serialize and preserve your context in the cloud. So there are a lot of transformational trends that will play a role in some way or another to this natural user interaction I'm going to talk about. If you look at user experience, there has been a lot of different waves, from the desktop to rich media to computer-mediated communication to search engine through which we have a look to the world. And we believe that this world is going to change to new modes of interaction where the context will play a central role, where you will be able to transform any surface and in fact any volume into an interacting environment. It means that we will enter in a more and more immersive environment, like we have always been trying to do through augmented reality since 30 years. So I will try to explain why I think that space is a new frontier. So let's start by trying to explain what we define as new UI, new user interaction. Our goal is to expand all the channels through which we interact with the machine. It could be multi-touch, gestures, voice and writing, eye gaze, and so on and so forth. Those techniques are supposed to be very easy to learn, even if we all know that the same techniques will not be usable depending on the kind of application we'll be using in the future. In order to be sure that those techniques are easy to learn, we want to try to mimic as much as we can the interaction in the physical world, which means that we'll be able to use pre-existing skills. So the goal is for users to avoid to learn a lot when using new interfaces. It's not a simple goal to reach, but it is very important. And using this context, I will go a little bit into details in a while. We hope to be able to create systems which are able to guess our intentions. So basically, try to predict what we will do next. And in fact, if you look at same thing, Kinect as a controller, as a sensor, it is always predicting what we are going to do, because this is the only way to cope with the video frame rate. And this is why we use machine learning in order to do so. So if we go through augmented reality through a very biased shortcut, we could start with the mouse invention by Douglas Engelbart in the Stanford Research Institute in 1968. So more than 40 years ago, the mouse was invented. At that time, it was made of wood, but it was the first time. Then we arrived to this Kinect, you are the controller, where in fact our goal was mostly to create a very easy to use device without anything to have to set up before using the controller, and at the same time being able to be as cheap as possible in order for everybody, or at least a lot of people, which means that we have to put in the device itself a lot of trade-offs, because otherwise we would have created something which would be much nicer, but also more and very more expensive. So if you want to imagine a future where basically your car drives and navigates for you, there are some very good prototypes running today, notably those made by Google. Your sound system, which plays music you love and only music you love. I don't know if it's a good idea, but that could be a goal. The phone, which rings only when you want to answer, which basically means that the phone is able to understand how you will react if you get a phone call when you are angry, as an example. All your family memories will be recorded automatically. Same thing, I don't know if it's a good idea, but that's something we could dream of. The fact that your body will be able to call the ambulance if you are ill, because you have some implanted biologically powered diagnostic sensors. And I will go a little bit deeper into that at the end of the presentation. Basically, in order to get there, your computer needs to know who you are. So your computer needs to answer a lot of questions like, where am I? Simple question. Who am I with? A little bit difficult, but can be answered. How am I feeling? Something a little bit trickier. Where am I going? It could be easy to get or to guess through my calendar, as an example. When should I go? As an example, my next meeting, same thing, could be known through my agenda, and so on and so forth. So in order to know that, we need to get sensors. Sensors are of both types, hardware and software sensors. So hardware sensors, you are using it anytime you get a smartphone, accelerometer, GPS, microphone, video, potentially physiologic parameters, something I will talk a little bit about. Software sensors, as an example, what is your device activity? How is your calendar status? Is it free or busy, or are you in a meeting? Your social networking presence. Did you register through Facebook where you are currently? And so on and so forth. The goal being to use this context to potentially embed intelligence in the computer system. Through sensors, you can create some kind of software abstraction where you will be able to store information and persist your context, potentially through some privacy policy which will control to which or to whom you are going to potentially share this context. Then we will move through an inference engine to an application whose goal is to embed the 5 senses to the application. So this is something which is easier to describe than to realize it, but this is the goal towards we are currently marching where. So basically, if I want to define what NUI is, it's both improved graphic interface through writing, speech recognition, touch, and augmented reality and context-aware computing. The goal being to create what NUI is, basically. An environment which is personalized, humanistic, context-aware, immersive, anticipative, and using and being able to interact with you through speech, vision, and gesture as being example. So this is the broad vision towards we are currently marching on. So let's try to illustrate what that means through some fun stuff, some more serious stuff, and through research stuff. So let's start by the fun stuff. As you can imagine, the fun stuff is through Kinect. If you move to something which is a little bit more serious, I'm here going to describe an application that is currently running in the Microsoft campus, where you are able to rent a shuttle or a car to move to any building into the Microsoft campus. So you just interact with the computer. There could be many people in the same room, and depending on the fact that somebody is talking or somebody is in front of the camera, we could imagine exactly who the computer is supposed to talk to. So let's show that in an engineering video where, so I don't know if the sound is sufficient because the voice is active, but here there is nobody in the room. Somebody is appearing and you can get all the information about the actor, what is his engagement state, what he's doing, what is the goal, what is the attention, what is trying to get. And the goal here is to interact with the computer. I don't know if you have heard building 44. So the goal is to get there from this room. So here you can see that the computer knows who he is interacting with, and you can get information and get your shuttle when you want. You can also detect what kind of wear the people is currently wearing, so you can get formal dressing and casual dressing at the same time by recognizing the fact that you wear a t-shirt or a shirt, and so on and so forth. So you get the idea. So the goal here is to show you what can be done just through context information. And in fact, there are a lot of things that could be done. So I'm going to skip the video because it could be using forever. And I'm going to share with you some Microsoft research projects. Some will be based on Kinect, some others will not. Those projects will be described through just a single slide, trying to explain what the project goal is, and then through a video showing you real example of what can be done through those projects. So the first one is called IllumiShare. So the goal of IllumiShare is to enable remote people to share any physical or digital object on any surface. As an example, through Skype, you can interact together anywhere in the world. And in order to do so, we have created a low-cost device which looks like a desk lamp, like a lamp that lights up when you are at your desk. And in fact, the goal of this lamp is to light up a surface on which it is pointed. And in fact, the goal of IllumiShare is to share a surface. It is as simple as that, but potentially to share any object in the physical and in the virtual world at the same time. So this is something that could be shipping soon because it is very easy to build. So I'm going to share with you through this video what could be done.
Hello, my name is Sasha Yunuzovic. I'm a postdoc researcher at Microsoft Research in Redmond, and today I'm going to talk about a research project called IllumiShare. IllumiShare is a project that enables people who are remote to do things together naturally and seamlessly. To do this, IllumiShare uses a camera and a projector combination. The camera captures the video of my surface and sends it to the remote end, to the remote projector, and the camera on the remote side captures the video of the remote surface and sends it to my projector so that I can see what's going on that side. What I have here is an IllumiShare device pointed down on my table, and it's currently illuminating an area in front of me, and this illuminated area is shared with my friend Keen, whose video you can see in the Skype connection in front of me. Now Keen could be really anywhere in the world, but for the purposes of this video, he's sitting right behind me so that we can capture his and my side at the same time. Now Keen and I are going to start off by playing a game of tic-tac-toe. I'm going to draw the board, and then Keen is going to start with his X in the middle. I'm going to put an O below it. He's going to go there, I'll go here. And you can see that he won the game. Now, in addition to drawing and playing games, we can also share objects that we have anyway that we want to either just talk about or play with. So, for instance, if Keen and I are playing a card game, I could throw down some cards, and Keen could do the same. He can also take some dice and roll them. And to make sure that I know that he's not cheating, he rolls them on his shared area so I can see the dice that he rolled. We can also compare objects such as toys. So I know he has got a Hello Kitty, and there it is. And I'm going to put my toy next to his Hello Kitty, and then we can talk about them and compare them. Another interesting aspect for LumiShare is that it enables children to get math or science homework help from a tutor who is remote. So for instance, Keen can be my tutor, and he's got a math homework worksheet for me through which I'm going to work. And so I'm going to say 1 plus 1 is 2, and 3 minus 2 is 1. And you can see as I'm working, Keen is evaluating my work, and 5 minus 2 is, I'll say, 3. And that's actually wrong. And so now I know as a child that I need to work on my subtraction of negative numbers. So what we've seen here is a LumiShare, which is an innovative device that allows remote people to share arbitrary physical or digital objects on any surface. It works well with existing systems for video chat such as Skype to provide delightful experiences through a hardware and software combination.
So it looks like a very simple example, but in fact it's not so easy to do because we need to fight video echo, and in fact we had to design some special chips that we have embedded in the lamp in order to get there. And so this is a very easy to understand project which illustrates something that can be used in our day-to-day life very quickly. The second one on which I wanted to spend some time with you is named Lightspace. So the goal of Lightspace is through the usage of multiple depth cameras and projectors to transform any room into an interacting and a fully interactive room. So in fact this is a working prototype I will be presenting to you. Anything is working and can be potentially be available very quickly. The only thing on which we are currently working is how to calibrate the 3D environment in order to be sure that when we have connected cameras and projectors, we have the right projection of graphics which are currently correctly mapped to the various surface which we use in this environment. So let me try to show you the video of this project. So there is no sound, so I'm going to describe it. So as you can see, there are some depth cameras and projectors that are just on the top of the room. And through this environment, we have been able to transform this table into an interactive surface. And our goal will be to interact between this table and one. So as you can see, we have been able, through touching the wall and the table, to directly connect and project the environment from the table to the wall. Here we are going to take this presentation and we'll keep it on our hand through this little light that is currently depicting on the researcher hand. So he's going to put this light on another surface, and the goal at the end will be to put this small light on the wall, where at the end the goal was to put the interaction on. So in fact, this project has been very successful and has been used a lot within Microsoft in order to do interactive design. And between now and the time it could be potentially shipping, we have to do both things at the same time, trying to miniaturizing the various sensors and projectors, and also to be able to do automatic calibration. And this is what is very hard to do. And this is what we have been able to accomplish through Kinect, as an example. So let's try to describe a little bit what Kinect is before trying to show you some research projects using Kinect. So as you know, it's a combination of RGB camera and some depth sensors. The goal being to get some depth information with this RGB information and some microphones. So if you look into some more details, there are essentially, beyond the microphone arrays, three cameras and sensors that are present on the Kinect. The first and the third sensor is what we call 3D depth sensor. So the goal is to illuminate through infrared the environment. The goal being to get through this illumination all the information needed in order to reconstruct the environment into 3D in real time. So what is in fact happening is we are creating through a class 1 laser a lot of very small illumination points, which are those dots which are projected on the people's hand here. And the goal is to detect what's going on based on the reflection it gets. So, in fact, we make sure that the regular RGB camera is held at a specific distance away from the 3D part in order to get a very precise alignment. And at the end of the day, we get 3D information and RGB color information in real time. RGB camera is basically a RGB camera, nothing special there. The goal is to enable facial recognition and many other things. And there is this multi-array microphone which is built of 4 microphones. The goal being to be able to figure out where the sound is coming on. So now I'm going to try to explain a little bit without going into a lot of details because I don't have the time to do it. How does Kinect knows what I do? So if you look at this gentleman is currently positioned and trying at the same time to give an order to the Xbox. We have to recognize in some way how the body is positioned in the space. So in fact we have created a very simple model of the body through vectors, which are in fact representing the skeleton. So in order to play and to learn how to do this, we have tried a lot of different ways of interacting through Kinect. Through various projects we have been doing since a while on object recognition, on human body tracking. In fact, we very quickly realized that we'll never be able to cope with our real-time goal, which was to basically be able to follow the human body as it is moving into space. So this is why, in fact, it was in 2008, the Xbox engineering group called Microsoft Research in order to help them. The goal being to be able to support all body motions, all agilities, being able to do it in real time for multiple players, and all of that has to be in 3D. So, as we didn't have any standard way of trying to get there, we had to try to use some other techniques, and this is why we get machine learnings to help. So in fact, during all machine learning process, we have to collect a lot of data. And the goal of those data is to use them in order to train a model, which is a model of the physical reality. So we collected a lot of data. So we visit households everywhere around the globe, filming real users. We use a lot of Hollywood motion picture, motion capture in order to generate a lot of computer graphic images. Then we get all the data and we try to overlay them in order to represent various position of the body in the 3D space. And we create this model through 32 body parts using vectors. This is why I mentioned the skeleton, even if it's not real bones. In fact, we just create a model of the body through this environment. And machine learning was allowed to determine a probabilistic cluster of body configurations, which could be consistent with those parts, even the parts moving together. And the goal being to present the most probable most probable next position to the user. So the goal is basically to anticipate on where the body will be one frame away, as an example. And so we used this model in order to train our machine learning model. And at the end of the day, Kinect was able to appear in the market. So we've got those millions of training images with millions of classifier parameters. It was something somewhat very difficult problem to solve, because we had to distribute the problem on a lot of machines. Here you have a view of some of the machines that were used at that time in order to create this model. And we had to solve some difficult decision tree in a distributed environment problems. So we had to create new algorithms to do so. But at the end of the day, we were able to solve this problem and to produce what Kinect is. So I'm going first to present to you a project also made by Microsoft Research called Kinect Fusion. So Kinect Fusion is a system that takes all live depth data, so in fact all the infrared generated information from Kinect, and to create in real time a high quality, geometrically correct 3D model of an entire room, as an example. So the goal in this environment is to use Kinect in order to scan any environment like this room, as an example, and to be able to reconstruct it within seconds. And at the end of the day, and I will show you in that in a demo, in a video. Unfortunately, I was not able to demo it. But if you want to see a real demo, I did a demo in Paris in February of Kinect Fusion, and it was a real demo running on stage. So in order to be able to do this real time, we need to use as much as we can the GPU engine. And in fact, we have done a GPU-based implementation for the camera tracking and the surface reconstruction. So we use a very high-range NVIDIA GPU in order to do it. And in fact, we interact directly with the rendering pipeline in order to be able to cope with the real-time goal. And at the end, it gives something like that. So on the left and down, you have the original scene that has been mapped through a 3D model texture using Kinect RGB data. So in fact, we superpose the infrared information, which gives the depth information, and the RGB output in order to match those two and to texture map at the same time in order to render it. So we are also able, through this model, to do some reconstruction, including augmented the lighting and to create a better rendering. We are also able to embed virtual sphere inside this environment, which is, as you can see, very, very close to the real environment. And you can even see that using this very fast GPU, we are able to include shadows of the physical environment on top of this sphere. So let's have a look to this on a video.
In this video, we show a new system which can create a dense reconstruction of objects and indoor scenes in real time. The only sensor in our system is a low-cost depth camera which is moved around the environment to be reconstructed. As this happens, the system builds and continuously refines a dense map, whilst simultaneously tracking the 6th DOF position of the sensor. Here, the dense model is rendered using Phong shading, and a normal map is shown alongside. A wireframe of the frustum of the Mobile Connect camera is also displayed. A relatively detailed model of an entire room can be generated quickly and easily. Here, the view from the connected device is shown at the top of the video, and the corresponding dense model is below. The coverage and fidelity of the model is continually being enhanced. If objects in the scene are moved, the model quickly adapts. When this box is added, the front faces appear almost immediately. Additional detail is filled in as data becomes available. A model which incorporates the detail of facial expressions and clothing is generated remarkably quickly and easily. Using data from the RGB camera, it is possible to texture map the rendered model to create a photorealistic look. Colours in the scene are refined over time as more data is collected. As these examples show, we get geometrically accurate occlusion handling. Here, a virtual shiny metallic sphere is added to the scene. We can also add artificial diffuse and specular lighting to the scene in real time. Virtual objects can interact with the dense model in lifelike physics-based scenarios. Here, we show the particles which are used to approximate the surfaces in the scene to enable real-time physics simulation on the GPU. We support interactions with dynamic scenes by deforming the relevant surfaces and any associated physics particles in real time. Movement of the Connect camera relative to the rest of the scene is continually tracked. Objects moving in the scene, even relatively large ones such as hands and arms, do not impact the tracking too adversely. In fact, we are able to build up and constantly refine a model of a tracked foreground object. By changing the reconstruction parameters, we can model fast-moving foreground objects while still refining the static background. In fact, such movements can be used to detect touch interactions with objects in the scene. Here we demonstrate this property with a simple augmented reality 3D paint application. When the Connect camera viewpoint is altered, the accurate registration of the paint of the scene is clearly apparent. In another interesting scenario, the system can be used with a fixed Connect camera and a moving object. Here, a model of a human torso is being 3D scanned. Objects which move in and out of a scene can be readily segmented by querying the dense model for changes. Once segmented, the object can be tracked independently, using the same technique that's used to track a moving camera. We demonstrate tracking here by re-registering the segmented object with the real-world object. Here, we track the movement of two depth cameras simultaneously to build up a single, high-resolution model of the environment in real time. Each camera tracks independently from a sparse model and contributes to a shared volume once correspondence between the two cameras has been found.
We've been able to show there that it is possible to scan an entire environment using a very low-cost sensor like Kinect and reconstructing in 3D the entire environment. So that was an example. Let's move to another example, which is a wearable multi-touch projector. The goal is to use exactly the same technology and to enable an interactive multi-touch applications on everyday surfaces. So the goal is very easy to understand. I'm going to show you the video.
Hi, my name is Gerber Banco and I'm a researcher here at Microsoft Research. And today I'll talk to you about the project called Wearable Multi-Touch Projector, which I did in collaboration with Chris Garrison from Carnegie Mellon and Andy Wilson here at MSR. This project is guided by the idea of being able to detect and provide touch and gestures, touch and gestural interaction on any available surface. So right now in our devices, most of the interactions, or actually all of the interactions, are constrained to a particular device form factor, to the screen of, let's say, a smartphone or a tablet. We wanted to enable the same kind of interactivity, but on any available surface, on your wall, on your pad, on your arm, any surface that you happen to have in front of you. To enable this, we created a combination of a Shotro depth sensing camera and a little Pico projector here, and this combination actually allows us to simulate these interactions anyway. So let me show you how this works. If you happen to be right in front of the wall, and if you want to get some interface there, you want to interact on the wall, all you need to do is just touch the wall, and you get something that could be actually on your smartphone, but it's not right now just projected in space on the surface. You can literally select an option from that, and then, for example, dial a phone number just the same way that you would on a smartphone. Another example is, what if we wanted to create something here? So again, touching this particular surface, you've noticed that the interface actually adapts to the surface size, and now we can use this to draw on this pad, for example. So it's not only one touch, but actually you have simultaneous multi-touch, just as you would expect from any touch-enabled application today. Lastly, I can show you another interface. No good touch application is done without maps, so let's do a little bit of zooming and panning to showcase some of that stuff. So again, the applications are just demonstrations of possibilities of what you can enable if you have touch and gestures on any particular surface. And for us, this is enabled by this unique combination of projectors and cameras that right now are worn, but we think they can be very miniaturized in the future.
So I'm going to end this presentation with two short videos using something we could call augmented human. The goal is to use contact lenses in order to do something very unusual, which is on the first video to get physical parameters from the tears. And in fact, we have been able to embed into contact lenses enough physiological sensors to get real-time information on a patient suffering from diabetes, and being able to put this information through wireless network to a remote computer. So let's have a look to this first video.
People were not convinced that this was doable. A lot of people considered science fiction. And Disney and Microsoft Research were early on convinced that this is a worthy cause. And they were willing to work with us and support us. I'm very grateful they did that.
My name is Kevin McFeely, and I was diagnosed with type 1 diabetes 30 years ago. My two children also have type 1 diabetes. I'm used to testing myself 6 to 8 times per day, but boy, when I think about my children, I mean, you have a spring-loaded needle that's coming into your finger, and it hurts them, and that's hard to watch sometimes. It's really hard.
What the functional contact lens would allow someone like Kevin to do, basically to pop this contact lens in and to never have to worry about measuring their glucose levels again.
We've been able to put a glucose sensor on a contact lens and show that it can detect glucose at levels that are found in the tear film. Our broader group actually has designed and built small radios that can interface with this glucose sensor and send out the information wirelessly.
Thinking about the functional contact lens for my children, I think that would be incredible. Monitoring their blood sugar through their tears as opposed to having to prick their fingers 6 to 8 times per day, that's really cool. And given that my children are diagnosed at such a young age, it does have the potential to help them live a longer, healthier life.
Whenever you work with very competent, informed, and capable people, you learn. So that really has been my experience working with Microsoft.
A world in which we don't think about physical or digital being different at all is one that I think we're marching towards and is really exciting to me.
I think what's really exciting about natural user interfaces is the fact that it will give us all enhanced lives. It makes us more of what we are.
So we have been tested this on few patients and also on animals, and the results of this research are going to be published very soon, 2 weeks from now. Which means that we'll be ready with the FDA approval to start real testing on the real patient population in order to be sure that we have the right correlation between the amount of glucose we get in the tears and also in the body itself. But if we are able to get some good medical results, it will be possible to ship this as a real solution within a couple of years. So the last video I'm going to present to you is in fact what we have started with using contact lenses. Because our first goal at the beginning was to do some augmented reality around using virtual lenses. And in fact, we have some problems, especially around potentially representing correctly with the right 3D environment, being able to be calculated in real time without any computer, which would be a little bit difficult to wear in such an environment. But we have done some good progress on that. So we hope to be able to present a live demo soon on that. But here is on a video what we intend to do.
Natural user interface, or NUI, as we like to call it, it's a new area of research where we're trying to really make the computer ubiquitous, trying to make it behind the scenes. You may be using it and you don't even know that it's there.
Imagine being able to overlay digital images on the real world seamlessly at any given time. I'm walking through the hallways of this building. You could overlay directions and arrow on the floor that followed me around the building.
When I walk into a grocery store, a natural user interface will be customizable to me. So when I walk in, the things that are important to me, maybe missing on the shelves of my cupboards, are the things that pop out at me.
Walking down the street, I could put people's names up, people that I recognize, people that I might want to recognize, information about them. The possibilities are endless. The project...
I think it was a good conclusion for this presentation. Thank you very much for your time. And I'm ready to take your question perhaps out, or I have 5 minutes. So thank you, Jacques. You can use French if you want.